Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last few lectures, we learned about the classical method of optimizing single variable and multivariable optimization problems with and without constraints. In this method, we learned that the objective function and as well as the constraints must be continuous in nature and differentiable. We also understood that in certain methods we have to identify the dependent and independent variables. We also need to identify if there are constraints, the active constraints and inactive constraints. So this process could be quite tedious, particularly when we have more number of variables and more number of constraints. In certain cases, when we need to do the second order derivative, we found that if we have constraints more than 3, it was quite cumbersome to come up with a solution. There is another concern with the classical method. Many of our real world engineering problems are not always represented as a direct function of the design variables, particularly whenever we are looking into the objective function and the constraints. So when this objective function and constraints are not explicitly stated as the mathematical function of the design variable, we cannot apply the classical method. In such situations, we need to use the numerical methods of optimization. In the next few lectures, we'll learn about the numerical methods of optimization for various different types of problems. So let's start with that. Before we get into the details of the numerical methods in optimization problem, first let us look into one of the real world optimization problem, which is difficult to express as an explicit function of the design or the decision variables. Here we are looking into a path optimization problem. A path optimization problem is a well-known problem in the field of robotics, autonomous vehicle and alignment development. In this example, I am going to speak in the context of alignment development. So when we are trying to develop an alignment for a highway or a railway project, we always have the start and end point. In this case, we have represented the start and end points as A and B. In between the start and end point, there could be various obstructions. In case of alignment, these obstructions can be in the form of water body, historic buildings, children parks, and so many other things. Our objective of developing an alignment is to avoid these obstructions and minimize the overall cost. In this particular example, we are looking into the horizontal alignment, which is in the X and Y plane. So if you are looking into the horizontal alignment, we are required to bypass the obstructions. And if you want to bypass the obstruction, we cannot have, in this particular case, a very straight alignment connecting A and B. Rather, we need to have a curvilinear alignment to avoid these obstructions. Now we can use as many as points to avoid these obstructions. However, our intention is to have the less number of points to avoid this obstruction, because if we want to have many points, then the tangent or the straight portion between the two curves are going to be less, and there are certain design restrictions of an alignment which says that there should be some adequate tangent length between two curves. In this particular problem, again we have considered two intermediate curvature to represent the alignment, and these two intermediate curvature are dictated by the point of intersections, popularly known as or commonly known as horizontal point of intersections for horizontal alignment. Let us say there are two horizontal point of intersections. Using those two horizontal point of intersections, we want to design a curvilinear alignment that can avoid point A and point B. So one of our objectives, if we want to keep it simple, is to find out the locations of these horizontal point of intersections so that we can avoid the obstructions. In this case, we have drawn three different alternatives. If we can represent the problem into a mathematical problem and then apply one of the optimization methods, then definitely we can find the optimum location of this horizontal point of intersections. Let us take the first alignment, the red one. The first point of intersection is the one where my curvature has been introduced, or where my deflection angle has some value. So along the tangent there is no deflection, but whenever we enter the curve there is a deflection. So if we extend our tangent, it will meet at a point, and this is my horizontal point of intersection 1, and the second one is here. Likewise, for the second alignment, which is here, this is the first horizontal point of intersection and this is the second horizontal point of intersection. In the third one, my horizontal point of intersections are somewhere here. So in all the cases, this horizontal point of intersections can be represented by the x and y coordinate. So we have two sets. So we have two horizontal point of intersection, and each horizontal point of intersection can be represented by the x and y coordinate. So if we say the first horizontal point of intersection is represented by x1, y1, and the second one by x2, y2. Our objective is to find out the optimum location of these 2 points such that the alignment cost is minimum and it fulfills the constraint, which is avoiding any of the obstructions. So the alignment cost, which includes possibly the length dependent cost and the land acquisition cost, we can easily consider the length dependent cost. So if we know the coordinate of this location or any of the locations, we can easily find out the length of the alignment by knowing the radius of the curve fitted at each of the location, and then understanding the length of the tangent portion of the curve and calculating that part, and then calculating the total length. So it was easy to represent if I know my x and y coordinate. However, the difficulty remains when we want to represent the constraint, As we said, we want to avoid these obstructions: water body, historic building site, children's park in this particular problem. There is no way we can represent the alignment mathematically to understand the impact or the effect it has on these restricted land parcels or restricted zones or the obstructions. The only way we can find it out is by laying out the alignment and then superimpose with the locations of these obstructions or the restricted land parcels and see if there is any overlap or not. So this process is done separately, and there are various softwares which can easily give us the feedback whether there is an overlap or not. So we see that we have an optimization problem in hand, which possibly we can easily represent in the mathematical function if we want to estimate the length dependent cost, but we are unable to express the constraint in the problem. And if we are unable to explain the constraint, we cannot use the classical method. Now let's look into little bit deep into this problem. We said we are only considering the length dependent cost. What about if we consider the land acquisition cost along with it? If you are looking into the land acquisition cost is not a uniform function, rather it is a very discrete. For example, a land parcel here next to the water body could be of higher value compared to the one which is nowhere close to the water body or any of the obstruction of any importance. So if an alignment by chance passes through this land parcel, the overall alignment cost just increases. If it passes through this one, the alignment cost is going to remain relatively lower compared to the other alignment which has passed through the high cost land parcels. And if we add all these things, we'll get the total land acquisition cost. There could be other land parcels along the alignments. There could be roads as well. And henceforth, we know that if you want to consider this is not continuous in nature. If you recall, in the classical method, again we said that the objective function and the constraints needs to be continuous, as well as in certain cases it needs to be convex. If it is continuous, then only we can easily differentiate and use the property of the first order derivatives to find out the locations where we can get the extreme values. So it is very clear in this type of problem, once we add the complexities, it is difficult for us to solve using the classical method. There are various ways of solving it. In certain ways, researcher had reasonably converted the problem into a mathematical function before solving it. However, there are a lot of approximation in the process, and hence we may not get the optimum results. In certain other methods where it is not converted into a mathematical function, rather it is considered as an discrete function or as a discontinuous function, and solve the problem using some or other numerical methods. So to solve an optimization problem using numerical methods, we need to have certain understanding of the objective function. One such understanding is related to the function nature. In this case, the function nature should be at least unimodal. A unimodal function is a one which has only one optimum value, indicating that there is only one global optimization point. There aren't any local optimum points. So a few examples of the unimodal function could be, particularly if my function is a continuous function. Here is a unimodal function. If we see, we have a very distinct optimum point, a minimum point in this case, and in this case the maximum point. A function could be discontinuous of this nature. A discontinuous function is difficult to represent in a mathematical format, but we can calculate the function values for different design variables values. So a discontinuous function of this nature can also have one distinct optimum value, and if we try to use the function values to find out the point where the function value is minimum, we can easily find out. A reverse of that is going to be at the optimum point. Likewise, my function values could be discrete as well. So a discrete value example which looks like this, we can clearly see that there is only one point where my function value is optimum, and in all other cases my function values are increasing. So in order to apply the numerical methods, we need to ensure that our function is an unimodal function. If it is not, if there are many local optimum solutions, choosing one of these numerical method may not work well. We may need to look into the heuristic methods. We can also apply the heuristic method in the unimodal function and obtain the optimum solution as well. If we want to apply the numerical methods, let us first look into the various options in the numerical method that can be employed. The numerical methods can be divided into two different types. One is the elimination method and another is the interpolation methods. In the elimination methods, we basically eliminate our search space gradually and come up to a range where our optimum point lies. So in the elimination method, we can have the bracketing methods. These are the crude method to find out the range where my optimum is going to lie. Or it could be region elimination methods, which is better than the crude bracketing methods in obtaining the optimum solution, but still we are not going to get the optimum value. Rather, we are going to get a range within which my optimum value is going to lie. And in many complex problems, finding out the range where my optimum value lies is good enough for the solution. The other method we said was interpolation. Now within the interpolation methods, there are certain methods which require derivatives and which does not require derivatives. So we can classify them, the methods which does not require derivatives and the methods which require derivatives. So we'll look into all these different methods one by one. So today we are going to start with the bracketing methods, and one such bracketing method is the unrestricted search method. In the unrestricted search method, we start from a point and try to look into the possible directions to see which direction my function value is improving. This is particularly helpful when we do not know the range within which my optimum value lies. In many cases, if we do not know, we can use this unrestricted search method to narrow down our range and identify the optimum point values where my objective function is expected to be optimum. So let us look into a couple of methods related to the unrestricted search method. The first one is the unrestricted search method with fixed step size. The unrestricted search method with fixed step size is one of the most elementary approach for finding the optimum solution, or rather the range within which the optimum solution lies, by guessing our direction from a initially guessed point. In this case, we use small step size depending on the accuracy we want and start our search for the optimum range in a chosen search direction. So this method starts by initially guessing a point x1 and setting the counter I to 3. At this point, we find out the objective function value, which is x1, and then we find out the next point in one of the predetermined direction from the initial guessed point. And this direction, we are choosing it as S, and the distance we are going to travel in that direction is decided by this step size S. So the next point x2 is going to be x1 plus S, and we find the objective function value at that particular point, which is going to be fx2. Once we find up to this point, we need to ensure that we are going in the right direction. For that reason, we are comparing the function value of these 2 points, which is x1 and x2, and then deciding what to do next. If our problem is a minimization problem and we find that x2 location, my function value is improving, which means it is lower than the or lesser than the function value at x1, then we are in the right direction. We should go to the next step, which is step number 6. In case if our problem is a maximization problem, and again we are in the right direction, which means the function value at fx2 is greater than the function value at fx1, then we do go to the next step, which is step 6.